Hi guys, and welcome to my second video on this KPS3010D power supply, and it's going to be a teardown. But first up, I have a correction to make. In my last video I complained about how the binding posts and nuts were made out of stainless steel and how bad of a choice this material is in this application. But today, or better the next morning, I discovered that the metal inserts look completely different from what I saw yesterday evening. So take a look for yourself. They are actually made out of nickel-plated brass, and that is the correct material to use here. So they have done a good job on the posts and nuts, and I have to apologize for my mistake. But how did that happen? The reason for my mistake was the light source. Yesterday I was shooting under an artificial light source, a fluorescent tube light bulb, which has a high output, but that light mostly consists of cold blue colors and is low on warm red colors. That light bulb made the metal look like stainless steel. I couldn't see a difference between the brass and the nickel plating. It looked the same. But under natural sunlight you can clearly see a difference, although to my defense this brass is very light compared to the one used on the other nuts, like this one from the Volta. This is quite a bit lighter, so that clearly didn't help. Anyway, I will have to do something about my light source, but for now let's get back to the video topic and tear this puppy down. And let's see what's loose in here. Yeah, this thing. What's that? That's a foam piece to isolate something. I think they didn't glue it in. This is, yeah, they didn't remove the paper back and didn't glue it in place. It was just loose in here, so yeah, that wasn't an issue if it would have stayed in there, but you never know. It's probably fell in through the slits or something like that. Possible. Yeah, but it's not great that it's in here, so great quality control, I guess, no? First thing, it's nice to see that they're using metal inserts on the plastic parts, so they don't wear out. I also like the construction, that the base metal plate is just a U shape, and they got the plastic parts in here, and that's clamped down so it doesn't fall out. This helps with manufacturing. Also a close-up of the metal case with the countersunk hole. Look how small that screw actually is. It nearly falls through. I hope it was worth it that they saved 2 cents on this application. Yeah, the screw nearly falls through. Yeah, that's bad. These screws are way too small for this. And at first glance, I have to say I really like the build quality of this power supply. We have locking varnish on each and every nut down in here. On the nuts and bolts fastening the fan. Also on the nuts at the output. There's also this locking varnish on every connector. Like on these, on the big ones down in here. The cables are all fastened down. Nothing is too long. They have a knot in this one to keep it short. These cables are fastened down so nothing flops about and catches an edge or rubs against something. So yeah, that's great. I like it. The board is also fastened down. They have holders on each side and also metal clamps on the bottom. They've also grounded the board. As you can see, there is a screw to the metal base plate, and there's a trace running through the clamps. That's also great. They also wired the earth wire properly. All the connectors are isolated properly with heat shrink. That's actually been heated so it doesn't move around. That's really not a given these days, as we have seen in previous power supplies. They're using the fuse. Yeah, at first glance I really like it. You can also see there is a temperature sensor on the heatsink. So the fan is probably temperature controlled, which is great for operation. So it's gonna be quiet when you're not using that much power. The cable for the output looks quite thick. There is actually writing on the cable. Let's zoom in. And as you can see, that's 750 volts and 1.5 square millimeters cross-sectional area. So this cable is actually good for 16 amps, which is good enough for this application because the maximum output is 10 amps, and it's really nice to see that they're using a proper wire. This is a close-up of the back of the board, and I have seen a few dodgy soldering points. Like this one, there is a little bit of a hole in there. This one down in here also has a hole in the soldering joint. There are a few of these in here, so it's not completely awesome, but yeah, it's okay. The soldering job is okay. It's not great, but not that bad also. One other thing I noticed, engineers sometimes leave the masking of high current traces, so during production these traces get an additional layer of solder on in here to increase the current carrying capabilities of these traces. So they left out the masking, but during production they didn't solder over these traces, so they are bare. There is no additional solder on them. Yeah, not great. One other thing I noticed is that the screws fastening down the heatsink are countersunk head screws. This is the wrong screw for this application. It should have been a flat head screw. And I'm wondering if these screws might actually fit the metal casing better. This one fits. Yeah, they fit in the metal inserts, so they have the same thread. And let's see if they would have been a better choice for this application. Yeah, these fit much nicer. Look at that. So they also had these screws lying around. They just, yeah, they chose not to use them. They should have used these screws for the metal casing and not to fasten down the heatsink. Next thing I noticed is that they have these rubber standoffs glued to the board. This is actually glued to the board. It doesn't come off easily. And the backside is sticky, so it sticks to the metal casing. There is also another one in here, pinched in. It isn't glued, but it's pinched in. So I guess it will stay in place, but they really should have glued that on. Doing good work and then messing it up. But there's also a rubber glued in the metal casing, so it pinches the board down, which is also great. So yeah, they have done some groundwork to keep it reliable, to keep the board from flopping about. So yeah, thumbs up for this. Another thing I noticed is that the board for the output connectors have 2 holes in them. I suspect these holes were designed for voltage sense cables, but they didn't install any. It would have made sense to detect the output voltage at the connectors and not at the back in here somewhere. So yeah, I think they left them out. Another thing I noticed is that from the looks of it, there is no power factor correction in this thing, which is really bad, like truly bad. Since 2001, in the states of the European Union, every switch mode power supply, which this one is, with a power output of greater than 75 watts, has to use power factor correction, short PFC. But I don't see one in here. So these are just the MOVs going to ground. This is a MOV for overvoltage. This is a capacitor. This is an NTC, which is an inrush current limiter. This is a common mode choke. And right after that, we have the rectifier. And after the rectifier, there is no power factor correction. There are just the storage capacitors for the transformer, which is this big one. The small ones are additional control logic power transformers. So they have decoupled the power transformer from the control logic, which is great because then they can control it freely. They can turn it off completely, which probably this on button does up front. And I don't know why they're using 2 of these, maybe one for the power board logic and one for the display board, but there are 2 of these in here. Yeah, and as you can see, no power factor correction in here. And this is a complete fail because without a power factor correction, this power supply with an output power of 300 watts is not allowed to be sold in the EU and is also not allowed to be used in the EU. Yeah, that sucks. That's really bad. So far it was looking so good and now I'm really disappointed. I will have to do something about that. Yeah. So what, I hear you ask? What is a power factor correction anyway? Well, I'm glad you asked. Well, there is a big difference in how these 2 power supplies convert the mains voltage to your desired voltage. This is an old school linear power supply, and it uses an old transformer, which is huge and quite heavy. And this is a switch mode power supply, and this transformer is a lot smaller, even though it has double the output of this one. So this thing weighs at least 5 kilos and this thing weighs 2 kilograms, so a lot less. And how are they doing this? The basic operation function is that this is working with the 50 Hertz alternating voltage from the mains, and this thing gets switched a lot faster, probably with like 200 kilohertz. And this presents an issue, and I'd like to explain that to you. So with the old school transformer, your input voltage and your input current are in phase, and the amperage amplitude is in direct proportion to the voltage amplitude, which is important for the harmonics this thing produced. As you can see, this is the first harmonic, this is the 50 Hertz alternating voltage out of the mains, and it produces very little other harmonics, like the 3rd, 5th, 7th, 9th. They're very, very small. So this is what you want, a clean power consumption. With the switch mode power supplies, you have an issue. There are spikes in the current. This is the input voltage, and this is the input amperage. The input voltage and amperage are in phase, but the input amperage amplitude is not in direct correlation to the input voltage amplitude. And this creates a lot of noise, a lot of harmonics. This is the full harmonic, and this is the third one, 150 Hertz. This is the fifth one, 250 Hertz, the seventh one, and so on. And they are in quite significant amplitude. A lot of these switch mode power supplies producing this much noise, this can add up quite quickly and present a massive issue for the power stations. So that's why the governing body in the EU demands power factor correction for switch mode power supplies like this one, with a power consumption greater than 75 watts. I've printed this out from the PFC handbook from On Semiconductor, and I'm gonna link it in the description down below so you can read for yourself. I wish the engineers designing this thing would have found this and read it and done it properly, but they didn't. And now I have an issue with using this power supply. And it would have been so simple, because in this paper even has an example of how to implement a passive PFC in a 250 watt power supply. This is a 300 watt power supply, so really close. And if you see, this is the common mode choke. It's this part in here. And after that, they should have just used another capacitor, a special inductor, 2 capacitors, and then use normal diodes for the rectifying, and also implement 2 other capacitors. So a total of 1, 2, 3, 4, 5, 6 parts, 6 additional parts. And yeah, they didn't do it. And as you can see in this graph, so the black solid line is the European limit, and this line is the noise with an easy to implement passive power factor correction. Now that I've shown you an example of a passive PFC, let's take a look at an active PFC from a practical application. This is a standard PC power supply. It was made by Be Quiet, which is a decent brand and has a maximal power output of 450 watts. Now let's take a look at what an active power factor correction might look like. And as we can see, there are some similarities in here. There's this capacitor, also like this one. There is a bit more input protection up front. There's a common mode choke in here. It's the same as this device in here. And after that, you can see that there is a rectifier, and after the rectifier, but this in here is the active power factor correction. It's something completely missing from this power supply, so yeah, I just wanted to show you what it doesn't take all that much. A few passive elements and a few active, and yeah, this is like $2 to $3 in parts, and that's it. It's really too bad they didn't do it. I would have gladly spent a few bucks more to have this comply to EU regulation. But yeah, it's really disappointing. There are a few semiconductors on the back of this board, like this one, this. There are quite a few in here, and also on the display board on this side. This is an ST microcontroller, and that's their value line. It's based on the ARM Cortex M0. It's a 32-bit MCU, which is quite powerful. It has 32 kilobytes of flash, 4 kilobytes of SRAM. It has 5 timers. It has SPI, I2C, UART of course. And at one off, you pay about $1.30 for this. And if you buy like 1,000 of them, you pay like 65 cents per chip. So it is quite cheap and also quite powerful. There is also a buzzer in here, but I've read in the manual that you can turn it off, so that's a good thing. Otherwise, this would have been a perfect opportunity to shut it up. I noticed this big hole in the power board, and for a moment I was wondering, why is it there? But then I realized this is where the display board must have been during production, because this outline matches exactly the shape of the display board. If you take a look, there are these notches up top, which exactly match this shape, and also these notches match the notches on the display board, as you can see. So this is where the display board was during production, so they can produce all the needed PCBs in one go, and that's a clever trick to save on production cost. So good job. Now I'd like to reassemble the power supply and see how it works. Now that I have discovered that the loose part was nothing major and I have reassembled the power supply, it is now time to plug it in and try it out for the first time. But that's gonna be in the next video, so please stay tuned for that. And in the meantime, as always, if you like this video, please give me a thumbs up. If you like to see more videos like this, please subscribe to my channel. And if you have any questions or comments, leave them in the comment section below. See you, bye.